captions work, because I have been putting the past couple of classes closed captioning. So let me know if you do rewatch the lesson, if the closed captioning works or not next time you watch a recorded lesson. All right, so let's go ahead and get started. There are going to be 5 parts to this unit. I took out a little bit, so this unit's going to be a little bit shorter than usual, but anything that's not here is going to be later on in the course. So I made this unit a little bit easier, but as a result, it's going to make another unit a little bit harder.
Yeah, but
so
it's after the break. So
after the break.
We don't care.
So the goal is to give you a simpler unit exam, hopefully, before the winter break. And then when we come back, we'll deal with future us. And remember that future us does have a quarterly when we come back from break. It will be, no, your quarterly too will be after break. Unit exam is before break. So like the exam you take next Wednesday is just on, I do need everybody to put it down. Thank you. All right, so your unit exam next week, to be clear, is just on organic chemistry. Just on what we learned pretty much through Thursday. Thursday will be that last full lesson of the unit. If we can finish everything we need to on Thursday, then Tuesday will be a day of review. And then next Monday will be a day of review, and then Wednesday will be the test. When we come back from break, not the class period we come back, but probably the second week we come back, will be your quarterly too. That will include everything from the beginning of the school year to where we got to when we come back from break. Pretty much. So the quarterly too is going to be hefty, and you'll notice that as we go through the year, the quarterlies have more material on them because it's supposed to be reflective of getting towards that end of year exam, where everything will be on the end of year exam. So without further ado, let's go over the Go work real quick. What I noticed, most of you did very, very well on the Go work. This is high hopes for me that you will continue to do very well when it comes to the exam next Wednesday. But the answer for the first one was position or positional isomer. Name A. Make sure that you put your A very clear. I am going to be picky because this is a written exam for Cambridge. If that is not an AL at the end, it is not right. Yes, Hakeem.
I was confused if it was butanol or butanol.
AL. And the way you can reconcile that, this is a carbon, right? If you put that this is an alcohol, like OH, you now have this.
That's crazy.
This should be CH2OH if this was an alcohol. There should be a hydrogen there and a hydrogen there because carbon makes 4 bonds. Whereas if you put that it is an aldehyde, that hits all 4 bonds. Right?
Yep.
So if this was CH2OH at the end, it would have been an alcohol. CHO at the end is an aldehyde. And because you got to be very clear here, make sure your A's are A's and your O's are O's. Just because that is a source of confusion. Yes?
I have a question. Can you do like long capital A? So that way.
Oh. I've never gotten that question before. I don't know the answer to that from a Cambridge examiner.
All capitals then? But like safer?
You technically could.
Okay.
You could. Yeah, in cursive you gotta be careful because your O's and your A's are gonna look very similar. Because like cursive O's is supposed to be like this.
Right, from the
A's
top.
like
Yeah,
that.
but when you're just running fast, it gets confused.
I know, my signature's terrible because I write it fast.
All
Alright, so go ahead. Let's go ahead and get started. I broke isomers into 2 parts. You're welcome. I did not overwhelm your brain on Friday, hopefully. Today we're going to be going over stereoisomers. So this is the more complicated of the types of isomers. You'll notice that I have made some molecules to help assist with understanding what's going on. It's the first time I've done this for this lesson, so hopefully it will help. Stereoisomers objectives, what we need to do. Describe stereoisomerism and its division into two types: cis-trans isomerism and optical isomerism. We're going to have to learn about both types of geometric isomers. They're called the cis isomer and the trans isomer. And explain the origin in terms of restricted rotation due to the presence of pi bonds. The pi bonds are back. Explain what is meant by a chiral center, and that such a center gives rise to two optical isomers. We call these enantiomers. Identify chiral centers and geometric isomers in a molecule of the structural formula, including cyclic compounds. You'll see some examples of that. You'll actually see a lot of examples in today's lesson. I made it shorter, but there's a lot of examples to look at for practice. And then deduce the possible isomers, which we'll see as well at the end of the lesson. We've actually also practiced with some deduction of isomers, but we'll continue with that. And so after today, we're technically through a lot of the intro material of organic chemistry. On Thursday's class, we're going to learn about the 5 types of major organic reactions. Just like there's 5 classics in inorganic chemistry, there's 5 classics in organic chemistry. So we're going to look at the types. What are the main types of reactions? And then we're going to look at reactions of alkanes alone on Thursday. So let's go ahead and go over the other bar real quick. I had to leave something out here because I haven't taught reactions yet. It says here, I do want to bring this up, draw 2 structural isomers. Some of you might have thought that this said to draw in structural format. It doesn't say. It just says to draw the structural isomers. It's just asking for you to draw the 2 isomers where the bromine has moved. You could have done this in skeletal, in display, or structural. It would have to say, draw the structural formula for the 2 structural isomers for you to have to do the CH3, CH2, CH2. So I'm going to write out this. 1, 2, 3, 4. My bromine is here. This is 2 bromobutane. And the other one is with my bromine on the end. 1 bromobutane. And these are positional isomers to each other. Yes? I had to be specific at the beginning to tell you that both of these were 4 carbons long, because technically you could have also had a chain isomer. What would be a chain isomer of either of these? Could we come up with a chain? Of C4H9Br? What would a chain isomer be?
Could it be negative 3 shaped carbons long and then a Br and a CH3 on it?
Like that, right? Or fully skeletal like this? Chain isomer? So chain isomer would have been changing the length of the carbon chain, whereas a position isomer changes the position of whatever group we're talking about. In this case, that group is a bromine atom. So just to be clear, do you have the pass to put back? Yes, please. Yeah. I thought, is this copy? Oh no, it's at the end. Okay, perfect. All right, so let's talk about stereoisomers. This is another definition you're going to have to memorize, and we're going to go spend a lot of time today, because I did break this lesson into 2, on what stereoisomers are. So first thing, stereoisomers are isomers in which all of the atoms are even connected the same way. But in 3-dimensional space, something is different. So remember when we look at isomers, something is the same and something is different. So in stereoisomers, we have the same molecules, same molecular formula, same even atoms are connected to other atoms.
Same isomers,
But
different.
in 3-dimensional space, there is something that is different. And so we say that they have different spatial arrangements. Spatial means different in some manner. So we are going to go back to talk about tetrahedral, and we are going to go back to talk about some of those shapes and bond angles we looked at a while ago in order to understand this. There are two types of stereoisomerism you need to be aware of, you need to be able to predict, and you need to be able to draw. The first type is called geometric isomerism, and in the purpose of AS chemistry, this is going to be present in some alkenes only. Alkenes are the only place you have to look for geometric isomers at the AS chemistry level, is what I'm telling you here. In the A-level chemistry course, there's also geometric and optical isomerism for transition metals. Believe it, I told you transition metals are crazy. They're about to start learning them in A-level chemistry, but there's actually also stereoisomers for transition metals. If you are a bio person, hemoglobin is an example of a molecule that has iron in the middle that has a transition metal complex that could have. Right? So present in some alkenes, geometric isomers. Optical isomerism, this means that it's going to spin differently. Spins differently when polarized light hits it. It's the molecule. You're like, what in the world? What does that even mean? And what we're going to be looking for that is a carbon atom with 4 different groups attached. That's going to give us something that has optical isomerism. Now, why does this matter? Specifically, the place where I can think that isomerism, stereoisomerism mainly matters is for those who wish to study medicine. If you wish to study medicine, either pharmacy or you want to be a doctor, or you just want to do biochemistry of some sort, one of the things you may remember is that you've heard of enzyme substrate complex, right? Where you have the lock and key model, and have you ever heard of lock? Do those words ring a bell? And so your enzyme has to be just the right shape, just the right structure to fit, to activate a site. Well, actually, molecules work like that too. Drugs work like that as well. They have to be just the right shape. They have to spin just the right way to activate whatever's going on in your body biologically, to activate a site. And so the three-dimensional structure of molecules actually completely matters. There is a chemotherapy drug called cisplatin. This version, meaning the cis geometric isomer, is what's used for chemotherapy. If the person who's the medicinal chemist accidentally makes the trans version, they make something toxic and not the actual chemotherapy drug. It won't help the person. It'll only actually hurt them if the wrong version is made. And so this actually goes a lot into medicinal chemistry, which is of course beyond the scope of the class, but if that's something of interest to you, this is definitely something that in organic chemistry and in deeper levels of chemistry you would see more of. All right, so what are we actually going to do with this? First, we are going to learn how to predict if we have geometric isomers. So the first type of isomerism is called geometric isomerism. So what I wanted to do, and this is kind of like just a class thing, I told you not to take those molecules apart, but you could handle them. Okay, I have them in the front. You should have 2 molecules in front of you. The color, blue, purple, green atoms are just supposed to stand for halogen atoms. White is hydrogen, black is, remember, carbon. So just to give you, that's some halogen. So color, halogen, white, hydrogen, just to understand how the model could work. Black, carbon, red, oxygen. Okay, so take a look at the single bond between 2 carbons. You have 2 molecules. Pick the one that has the single bond between 2 carbons. I want you to spin around one of the carbons. Just spin it. Spin around one of the carbons. Hold one carbon in your hand, spin the other. Does it rotate? Do the atoms rotate?
Yes.
So you can put your 2 halogens right next to each other, You can put them opposite to each other. This is what we call free rotation. Just like my arm, I can go like this, right? Free rotation. Your atoms can spin when you have single bonds. Now take a look at your other molecule that was provided to you. With the two lines representing the double bond. Try to spin around a carbon here. Try to spin it. What happens when you try to spin it? It doesn't move. Yes, sir, what do you need? How much? Because I need it for something for next week. Everyone's always taking my stuff. Pick one or two. Stop taking them apart. Were you able to spin it?
No.
Not without breaking the bond, right? You have to legitimately break the bond to move things around. So the idea is that these halogens are stuck up here, right? And these hydrogens are stuck down here. And you can't take this halogen and move it down where the hydrogen's at. Whereas in a single bond, you can totally do that. So far, so good? All right, so let's go with this is. In a double bond, the key words here, there is no free rotation. The atoms are stuck in place. This matters because there are two possible variants around a double bond alkene you could have when you have different atoms. Your group has one of the variants, and I'm holding the other. And I can't turn to go from one to the other. These two variants are called the cis variant and the trans variant. This means that your two groups are on the same side of the double bond. So this activity is to help you see this three-dimensionally. So what I'm holding here is a cis molecule because my groups are on the same side of the double bond. So what you're going to want to do is hold your hand to the double bond flat. You compare your groups above and below. If you have the same groups on the same side of the double bond, you have the cis variant. And if they're on the opposite side, you have the trans variant. And you cannot turn a cis variant into a trans variant unless you actually physically break the bond, which means do a chemical reaction to do that. And so trans means opposite side. So groups are on the opposite side of the double bond. By the way, in organic chemistry, most of the professors I've ever had have suggested that students buy a molecular model kit because it actually helps to see what's going on when you build the molecules, actually. So I'm holding a cis variant. What's yours? Cis. What's yours? Did you originally have cis or did you change it? What's yours? Trans.
Oh, we
What's
had that
yours?
one. We had trans, yeah.
Cis. What's yours? Trans. Cis. Sophia. Can I see it? That is not the right molecule to be holding. It's the other one. That has free rotation. Trans. And Mariani and Janie, what do you have? Cis. Go to where the double bond's at. Notice the two, hold it where the carbons are. Straight where the carbons are, you put your hand through like that. That's the dividing line. Both your atoms are on the same side of that double bond. You have the cis variant. All right, so another way that, I don't know where I I picked this up. I must have been in class somewhere. And I guess I'd say maybe don't do this on a Cambridge test, but if you do it next week on Wednesday, I'll understand. Okay, so another way to do this is you can do something with your hand, and this is totally for chemistry. Go ahead and put your one hand like this, where these two fingers represent a double bond. It's not what you think it is. And your thumb, stick it up. Take your other hand, right, and do it again, and put them next to each other. You have what is called this variant right now. If you turn this, what do you have? Trans. So if you didn't remember, cis means same side, your thumbs are on the same side. Trans means they're on the opposite side, diagonal. So cis and trans. This will help you when you're looking at molecules. Is this cis or trans? It says it here, but like your groups are on the same side of the double bond.
You always have to write this right.
You will have to name it, yes.
Always. Right, yes.
Yes. And then this is trans. Yes. Go ahead, drop your chest. So that is a way, albeit, like I said, I might not suggest doing that on a Cambridge exam, but it actually works. If you hold your hands up, you can predict for more complex molecules if you have a cis or if you have a trans. You can just put your fingers to it. All right, you could do that, like just on the paper. You're holding. All right, so
That's only for the isomer.
this is for the geometric isomers, yes. So notice, if your groups are on the same side of the double bond, you may want to circle that here. You can also look at opposite if your hydrogens are on the same side. We call this the cis isomer. The trans isomer would be when they're diagonal from each other. Now there's something that I have not mentioned yet. If you have this situation, if you have this situation, this is neither cis nor trans. This is neither cis nor trans. Now let's pay careful attention to what's going on here. You can, if you want to, you can split it apart, break it, but you have to break the bond, right? You physically have to like go, bam!
She told us not
Chemical
to break it.
reaction.
It's a trick.
It is a trick.
You get tricked.
So watch what I've done here. This is not cis or trans. If I do try to mix these and put this on the other side, it's not going to change anything. Like if I switch this with this, it changes nothing. So if I have two of the same group attached to the same carbon, two of the same group attached to the same carbon, attached to the carbon of the alkene, there is no stereoisomerism here, no geometric isomerism, because you can't get another variant out of it. This actually tells us something really important. If I have an alkene like this, and this is skeletal form, I apologize, I just don't like to write. What does that tell us about an alkene at the end of a molecule? How many hydrogens are on an alkene at the end of a molecule? And aren't those two of the same exact thing? So terminal alkenes is the fancy terminology. Terminal means end. Have you ever heard of terminal meaning end before? Terminal.
Terminal illness.
Terminal illness means end of life, right? That got really dark really quick. It actually means terminal end of like a chain of carbons, right? Terminal in DNA. Studying DNA right now, I know in ACE Bio. Terminal means the end, right? 5 terminal, 3 terminal, the ending. The terminal carbon A terminal alkene has no stereoisomerism because it's got two hydrogens on it always. That's a quick way to look at a molecule and know no isomer here. Because it's got two hydrogens on it. Even if it's drawn in the skeletal form, it's got two of the same on it, no cis, no trans. You have to have one group on each, and they're either on the same side or they're on opposite sides. The molecule kits are to help you to understand what's going on. So what do I have here? Trans. Another way of saying this is going back to my fingers. I can't have two thumbs on the same hand. It is just not possible. So when I look at cis and trans, they either have to be on the same side, different carbons, or opposite sides, different carbons. Yes? Different hands, opposite sides, same side. You can't do it. Stop. It doesn't work. All right, take a look at these examples here. This is another way of looking at a cis isomer. This is cis. Do you see that? This is cis. Point it out. These are the two carbons, and the groups are both facing up. That means same side, right? Whereas here, draw a line between the two carbons. One group is going down, the other group is going up. That's opposite sides. Just like this, right? That's trans. So you may have to, for larger molecules, interpret if you've got the cis isomer or if you have the trans isomer. And so these are the geometric isomers. One version is cis and one version is trans. And so we look at two different types of isomerism today. And so they're actually all the same atoms connected, right? They just differ in three-dimensional space. This is just to bring up the different molecules. There's more information in there than is necessary. We're not going to use syn and anti-vocabulary. This is just to give, to look at information here. Name the following compounds. This is what we actually have to do. So, here's an alteration to naming you have to know. If a cis or a trans variant is present, you have to say which one you have. If cis or trans variant is present, you must state so in the name. And that's part of the mark. And the way you do it is you put cis in the front or trans in the front of the name. That's how you would alter the name.
Oh yeah, because
So,
it's 19 because it's a double bond.
how many carbons do we have here? 1, 2, 3, 4, 5, 6. It's got a double bond, which means you have to check. So now it's on you. If you see a double bond, an alkene, you must check to see if it exhibits cis-trans isomerism. Well, how do you check that? So if you have two groups coming out, you would check around the two carbons. If you have two groups coming out of the same side, you know that it's. And if it was flipped the other direction where these two groups were coming up the top, it would be the trans variant. What if you had this? 1, 2, 3, 4, 5, 6. Would this have cis or trans? No, because the alkene's at the end. Good. Okay, so this would be called what?
Cis 3.
And then 1, 2, 3, between 3 and 4. Cis 3 hexene or cis hex 3 right? Hex 3. And this is just hex 1 E, just to be clear. Right? All right, how are we feeling so far? Okay. All right. Next one. What's this?
Oh.
Carbon, carbon. Is this a cis or a trans variant?
Trans.
It's trans. They're diagonal from each other. One goes up, the other one goes down. This is trans. So trans what? Trans 2 hexene, correct. Because it's between 2 and 3. Here comes another question before we go further. Does this have cis trans isomers?
Yes. Yes, it does. That's that final answer.
What's this? Does this have cis trans isomers?
Yes.
If you've got 2 of the same group attached to the same carbon, there's no cis trans isomerism, right? So no geometric isomers here. So what would the name be? Okay, so butylene 2,3 dimethyl butylene. Yep. Oh,
You do 2, 3,
1, 2,
dimethyl, 2,
3, 4. Yes. Go ahead, Jess. Either is fine. Both are accepted. Hextulene or it's this one would have been hextulene the other way, and this one would be 2-butene the other way. Either way is fine. Yes. Because I'm showing both.
So we put since two from any
No cis here. No cis. We cannot say these groups are cis to each other or trans to each other because they're both, so they're neither. Because you have the same carbon, this carbon, right? If we drew it like this is another way of looking at it. These are all the atoms drawn out. Right? This carbon has the same 2 groups attached to it. Because it's got the same 2 groups attached to it, no geometric isomers. Nothing. Now, all right.
They're on the same side.
There's actually another type of question you could be asked that I want to address because I am taking this lesson a little bit slower. And it is a type of question I'm sure I'm going to put it on next Wednesday's test. And it's going to be on paper 1. The paper 1 part, the multiple choice part, because I've seen it on a lot of old tests.
They're on the same side.
Can I discard this? I want to show you something. If you've got space somewhere, I have a question. How many isomers that are geometric are possible? Hold on. In this molecule.
Oh. I said
Okay.
either trans.
God damn.
I've seen a question just like this. It's not the exact molecule, but on paper 1 several times. So you may want to write it down.
It's at the end.
1, 3, 5,
It's either 3 trans
7, none. It's none. And then CO.
It's either none or
So how would we approach this is the question. First thing, every time you have an alkene, you should check to see if it has geometric isomers. The alkene between carbon 1 and carbon 2 has 2 hydrogens on the end, right? It's terminal. So there's no isomers on carbon 1. No isomers that there could be, right? What about carbon 3 to carbon 4? That's trans, that's the trans variant, but couldn't it also have A? Because it said how many isomers are possible? Like, right? So if it has a trans variant, that also means it has a cis variant. So every time you have the possibility for a geometric isomer, you have one, that means you have the possibility for the other one. So a trans version and a cis version. So the best way to approach this is every time you have an alkene that has a cis trans variant, you have two possible variants. So then how many isomers are possible for this molecule? Correct. That's the correct answer. So the way to approach it, this again would have the trans variant. This is the trans variant, but it also has a cis variant. And then this last one here, trans then cis. What if we wrote them all with the cis version? What would that look like?
Is AB and B. They do one of those weird thing.
Weird.
You know what I'm talking about.
You could go like, I mean this, and do like that, right? Same side. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then I guess you could do this and then like that, right? And then you could do this and then like that, right? And then 1, 2. Does that make sense to you? These are all cis. These are all transes. Those are 2 of the 6 possible variants because it's just like the combination you could have. So every time you have a site where you have a cis trans isomer, you multiply by 2 for the possibilities. So here the answer is 6 possibilities. And this is the way that they ask it on paper 1. They'll give you some crazy long molecule and they'll ask you how many isomers are possible here. And so you look for your double bond. Don't include the ones that can't have like a cis trans isomer, and then you multiply by 2. That's all you gotta do. Yes, Justin. Yeah. It's just completely cis. But then you could have like one that's cis trans trans, trans cis trans. Right. So you have to look at what's going on around this specific area. If one's going up and one's facing down, that's why I said it's helpful to have like things to help you understand. If I put my hand to this, I can see that this is trans right here. Right. You look at the immediate area of those 2 carbons. All right. So with that being said, let's take a look at some practice questions on this before we get to the other type of isomer. This is from a 2016 exam, but it's still relevant. They could ask this. The question is about molecules with the molecular formula C4H8. C4H8. What's a pair of positional isomers with the formula C4H8? First of all, how do we know what type of molecule C4H8 is? Is that an alkane, or an alkyne? It's either an alkene or it's a ring. Yeah? Right? You have to remove 2 hydrogens. Positional isomer, C4H8. What does position mean again? Change the position of what? The double bond. Because that's the only functional group here is the alkene. So you will have one that's this, and one that's this. So far, so good? We okay with this? Watch again. Did I have to give the structural formula? Did it say here, give the structural formula? It did not. It just gives the structure. I know that I've had so many students get confused on this. It literally has to say, give the displayed formula, for example. It'll say it like that, displayed formula, for you to have to write it out in the way they're telling you to. If they just say give the structures, but they don't tell you which type of formula to write, your choice. If you like to do everything displayed, feel free. I will count to make sure your carbons do not have the wrong amount of bonds. If you, just be aware if you draw displayed and you mess up on one of those carbons, it's wrong. Same thing for structural. If you pick structural and and you have one too many or one too few hydrogens, it's wrong. That's why I picked skeletal, because like there's less of a chance to go wrong with skeletal, just to be clear. One mark here. Give the pairs of
That's wrong.
chain isomers with C4H8, and neither of them
Yeah, that's probably right. You're probably right. It just looks stuff. That's what it's done.
All right, just hold on. Is that emergency? Okay. C4H8 that do not exhibit stereoisomerism. This makes sense so far?
Oh, so you are the okay.
Neither of these have stereoisomers. And they are chain isomers of each other. One mark. Yes, good. Ready for the next one? Structures and full names of the stereoisomers with C4H8. Now this is on our new lesson. What are the two stereoisomers? Yes. What are the two stereoisomers? Give the structures and their full names. Be filling that out. But do you need to go back?
Let's go with cis. And then we'll go two. Easy? Easy. Two. Sounds right.
Good? And then real quick, the last one.
You're supposed to draw it?
Structure. Trans,
There's position, chain, and function.
2-butene or butylene.
See, but now I'm right. I actually just got it.
Either down or up, doesn't matter. 6, 2, butene.
Oh, that's only why they have the chains and the you know how to draw it. Yes, that makes sense.
All right. Are we good with this?
If you put two butene, it could be either.
All right. Ready for multiple choice? Okay. We'll come back to this one. Let's do. Yeah, we'll come back to this one at the end. Does it? All right. Let's do the second type of isomerism, and we'll come back to that. Optical isomers is the second type. So the first type of isomer is called geometric. The second type is called optical isomers. Yes. So I'm going to pass out the model kits at this point. How much fun there was.
Functional isomers means the functional group changes. Chain isomers. The functional group changes.
And here we go. You're getting part of the kit. Don't do anything with it yet. Soon. Don't touch it yet. Against your better judgment.
Don't touch
Don't touch it yet. Okay,
Never watched Nemo.
here's your instructions.
That happens in like the first 30 minutes. Never seen it. That was the start. The title. They don't say no.
They say what for things.
But, well, that's what I said.
Yeah, but.
Oh, transfer.
Build
All right, instructions are up on the board. Build a molecule. Carbon is black sphere. You gotta attach carbon to 4 different things. 4 different things. If there's 2 of you, each of you build a molecule where carbon is attached to 4 different things.
What's the yellow?
That's not something we're gonna use. I've got 6 openings. Sulfur.
How many carbons?
That's totally green. Oh, there's also a purple one.
No, it has to have 1 opening. 4 different things. It has to be something valid.
Oh, this gray one also doesn't exist. This is one word, and now this blue one has 4 openings. I promise it has 4 openings.
Yes. 4 different things, but they're like things that have openings.
No.
So if you have oxygen, you also need to do a hydrogen.
Can I have
Like
the
you
purple
have
one?
to do OH.
Can I steal a purple one?
Yeah.
One, the purple one.
How many openings do you have? How many openings? Give them 6.
Can I borrow? You can't use those, right? Because they
They're
have,
all the same.
no, because they have multiple openings. And it's all the same.
Alright, I'm giving you a couple minutes. Build a molecule where carbon is attached to 4 different things. If there's 2 of you at your table, each of you build a molecule. There should be no opening. I advise things like oxygen, where you can do OH, maybe methyl groups. What's that?
What that?
This is not 4 different things. These 2 things are the same as each other. This is 3 different things.
No,
This is 2 of the
We
same.
don't have 4
It has to
things.
be 4 different things. You have to come up with 4. Get creative. Get more creative. You have to use the single bond, not the double bond. Single bonds only.
Stop doing things.
The single bonds are the short ones. Pick the short ones. I'll check in a moment. Let me just check something real quick.
Yeah.
Yes. Thank you. Follow the instructions on the board. Follow your team. You each need to build one. Have we built? All right, let me check. Hold on 1 second. Okay. Oh, you need the short one. Let me get You may need to get from your friends in the other group on your table. There's also a bunch of single bond connectors over here. I'm gonna take some here. That is not what I'm looking for. A carbon attached to 4 different things with single bonds.
Oh, that's like crazy.
Here.
You know what I mean?
Alright, your carbon,
Do you get what I mean?
this is not because it has to connect to a hydrogen. You need another single bond.
Okay, I get it. Look at mine.
No, my bond.
Does this count?
Here.
Did I do it?
Let me think.
Did I do it?
My bond.
Okay, this is something crazy.
You made it.
Yes? Alright.
What do these little stuff represent?
You don't need to. They're for space filling models. They're not for the bond. That's all. Words.
So we're saying how? If it didn't even go, because it did. I'm tired of this right now.
Alright. So, at this point, you have 1 more minute to attempt your molecule with 4 different groups. Got it?
Can you touch a carbon and rub it in again?
Yeah. That does the thing.
How did we get this color?
It does the thing.
What are those?
Alright. 15 seconds, then I need your attention again. The kids are fun. Alright, so
Like, if you had to take so much from them.
here's the deal. Around the carbon that has 4 different groups, when it's exposed to light, one version of it will spin clockwise, and the other version of it will spin counterclockwise. We call these optical isomers. And so the requirement, optical isomers, there's a fancy name for them. You should underline it. They're also known as enantiomers. Enantiomers. And what this means is that any molecule that has a carbon on it that has 4 different groups, meaning that carbon is attached to 4 different things. If polarized light, and you use a device called a polarimeter to prove this. We don't have a polarimeter in this school, but you could prove it with a polarimeter. And it'll actually, if you have the one variant, it'll spin clockwise. And if you have the other variant, it'll spin counterclockwise. And so, in order for this to happen, you have to have something called a chiral center. And this is fancy terminology that the carbon has 4 different groups. So I've built one, and you'll see if yours is reconciled with this. My carbon that's chiral, what I decided to do was to put an OH, that's one group coming out one end. I have a hydrogen. I have a halogen, which is the green one, and I have a methyl group. Those 4 groups are all unique and different than each other. If I were to draw this on the board, it would be this. C, CH3, OH, fluorine, and hydrogen. Every single one of these groups are unique and different from each other. You will be asked to identify chiral carbons in molecules and to draw them correctly, and to draw both isomers. So there's more to this. In order to understand this, because it is a different 3-dimensional spatial orientation between the two, the way that we often describe this is the same way to understand your hands. Like what? Look at your left hand. Look at your right hand. Right? They should be what we call mirror images of each other. But if you were to try to put your left hand and your right hand one on top of the other, what you notice is your thumbs stick out of different directions. They're facing the opposite direction. And that's the same thing, the same way to understand chiral molecules. They're all connected the same, but in 3-dimensional space, they're facing opposite directions. And so we're gonna move on shortly to what we actually need to do with this. I know you're all with the model kits. Put them down for a little bit. The faster you get through it, the faster you get to play with them again.
It's like merge them together.
Later. Did you get this down? All right, put them away. For now. We can build them later. I know it's like Lego. Give me quick later. It's a fun time. All right, I'm leaving this up for about 20 more seconds, then I'm moving forward.
Alright.
Let me try. That is cool. All right, moving forward. So,
Left hand version.
chiral molecules have what we call a mirror plane, meaning the same way that your left hand and your right hand are images of each other, mirror images, the two variants of the optical isomers are mirror images of each other, meaning that the carbon in the middle is attached to four of the different things, but how they're oriented in space is opposite of each other. And yes, you will be asked, and we're going to see a question in a little bit, to draw both versions. And you could, afterwards, build both versions with your molecule set. All right, so far so good. Oh, another way to say something is not chiral is achiral. So achiral means not chiral. The A in the front is like just synonym. A means opposite. Achiral, not chiral. Asymmetric, not symmetric. Another example of that. Right. Two molecules that are mirror images of each other. The important thing is that if you put polarized light to them, they spin differently. This matters because if you have a drug, one version will spin into its target site clockwise, the other one would spin counterclockwise, and that will actually matter whether that drug is effective or not. It's kind of like a screw, right? It has to screw in the right way. So, what are you going to be asked to do? First thing you're going to be asked to do is in a molecule, find the chiral carbon. I've given you a carbon chain that is 6 carbons long. Can you identify, given this carbon chain, which carbon is chiral? Remember, chiral means 4 different things. We say 4 different groups is the Cambridge terminology. 4 different groups attached. I heard someone said 3. Let's check it. On the top, you've got CH3. On the left, you've got CH, CH3, CH3. Right? That's a group. Do you agree?
Yes,
Is this group and that group the same? We need 4 different groups. All right? What's coming out the bottom of this? Is that exactly the same as this?
No.
Is that exactly the same as that?
No.
So it's different. It's a third unique group. And what about this? So circle each of the sides around that carbon.
Do you make them in 2 different? How do you know which one?
You look at everything coming out of that carbon. Left, right, top, bottom.
How do you
Technically, you should analyze that for each carbon. So somebody suggested carbon 3. And another way of looking at it is, where there's the most stuff going on, that's probably where you should look first. Where there's the most stuff going on. That's your most chance of getting different groups. But I'm going to discard this so I can show it to you again from scratch. What if we analyze carbon 1? Carbon 1's not chiral. Why not?
It only has one group around it.
It has 2 unique groups. One is hydrogen, and the other one is all that stuff. The way to understand it is carbon 1 has a hydrogen, a hydrogen, a hydrogen, and that.
Wait, so
Group. than each other groups of atoms or different atoms around the carbon. And that will give you the two variants, one that spins one way, one that spins the other. Achiral compounds do not have different variants. They don't have stereoisomers. So then carbon 1 not it. Agree? Why isn't it carbon 2? To be clear. Because if we analyze carbon 2, you'll see again, and this is why pencil's good. You like pencil? Pencil's good for something like this because you can check each of them. On carbon 2, you've got this, you've got this, you've got a hydrogen, right? And you've got all that. Are there any groups that are the same as each other? And once you have two groups that are the same as each other, it has no stereoisomers in there. No optical isomers, no chiral carbon. Carbon 3 I've already checked. We know that it's two center. Yes. Yeah, go ahead. All right, are we okay with this? With it being carbon 3?
Three-dimensional, you have.
You should build them after. All right, so let's check this one out. Yes? We're ready. Prepare yourself. Here's corticosteroid. Anybody in biology studied steroids? Steroids, you always have 3 6-membered rings and 1 5-membered ring. So this is an example of a steroid. Corticosterone is a hormone involved in the metabolism of carbohydrates and proteins. Cambridge always loves giving you them fun facts, especially in the organic area. You're going to read all about like the smell of leaves and stuff because it's different compounds. But the question asks, how many chiral centers are there? What are they asking?
How many chiral carbons?
Yeah. So they're really asking, and you want to point that out for yourself so you understand the terminology here. When they're asking chiral center, they're asking how many carbons here have 4 unique groups attached to that. Are there any that we could take out that definitely aren't chiral?
Wait, but how do chirals the one that's cycles? Those pips, the ones that CH3, the ones that we have.
Okay. So let's take them out, right? X. Any other carbons we can take out of this group?
The ones that are double bonded cells.
Because there can't be 4 different groups because there's only 3 different groups, right? So bi. Anything else you could take out?
H's.
Well, they're not carbons, so sure.
Elimination.
You can. So what's left? Let's take a look at the carbons in the ring. This carbon right here. It has 2 hydrogens. Take it out. Do you agree? This has a hydrogen, and then this stuff, and this stuff. And although this stuff in this order of atoms is not the same as this stuff, so symmetry will come into play. The 2 hydrogens are the same, so take it out. So that means any of the carbon atoms in the ring that have 2 hydrogens cannot be chiral. So can we take out that hydrogen? All of these, right? Goodbye. All right. And this one. Goodbye. All right, so let's see what we're left with. Is this carbon unique? It has 4 unique groups. It's got a CH3 at the top. It's got that stuff that way. This stuff or this stuff this way. And that stuff that way. And you have to understand that all that stuff is different. Like the atoms are not connected in exactly the same way in large molecules. Not symmetrical. So this is our first one that I identified. Well, apparently the answer is 5, 6, 7, or 8. So there's more.
5, 6, 7. Final answer.
This one. That chiral. That stuff, and a hydrogen, right? That's 2. Any more?
Yes.
This one. That stuff, and 1 hydrogen. That's 3. This one. That stuff, that stuff. They're not all, the atoms are not connected in the same exact way in any of those three directions. Do you agree? They're all going to different things. It does. That's why they analyze one at a time. 4. What about this carbon? OH, H, that stuff, 5. What about this one? CH3, that stuff, 6. And what about this one? Hydrogen, that, and that. The answer is 7.
I think the best way to start is just get rid of the ones that have double bonds
Get rid of the double ones,
and the ones
get rid
that
of the ones that have 2
two
hydrogens, and count the rest.
and then
And
the
that's
rest,
pretty much it.
and then the rest,
Rest
is
of
just
the
looking
carbons.
for symmetry.
Right. Just double check symmetry because remember, if you've got something like this. Let me give you something. Are there any chiral carbons on the molecular drawing?
Yes, there's one.
Where?
There's exactly one.
Are there any chiral carbons on the molecule I've drawn?
Yeah, the one right above the weight.
Is it
One carbon to the left and one carbon.
Oh, never mind. Those are two series.
CH3? Wait, so is it or is it not?
No, it's not.
It's not. OH. And then CH2, CH3, right?
Doesn't.
It's not chiral,
No, I didn't really look at it.
right?
Yes.
There's no chiral carbons there. That's why you should always check. In the one I drew here, I'm going to just redraw it. This group is the same as that group. They're both of CH3. Those are the exact same atoms. So not chiral. There's no chiral carbons here. No chiral carbons. You need 4 unique groups. That's what you have to be able to visualize here. Aren't you glad I broke this into 2 lessons? Last year I taught this in 1.
I mean, this.
It could be done in 1, but you gotta like,
You mean like the ones with this glass glass?
yeah, and this. They didn't get like as many molecular models. You got all the models. All right, so let's take a look at another question. Which compounds here then would exhibit stereoisomerism? So let's go ahead and review before we answer the question. When they say stereoisomerism, so you may want to write this flowchart down for yourself. Stereoisomerism. There are 2 types to look for. What was the first type?
Geometric.
The 2 types are called geometric, which we also know, and they also, I've seen them on mark schemes exist, accepted as cis-trans, if you write cis-trans. And the other type, which we're learning now, is called the optical isomers, and what we would be looking here are the chiral carbons. So these are the differentiations in 3-dimensional space that can take place. Either it's across the double bond, so we would be looking for geometric, we'd be looking for alkenes. And for optical, you're just looking for a carbon with 4 things, right? X, Y, Z, sure, A. Like, just pick a letter. They gotta be 4 different things from each other. Pick J. You know there's no J on the periodic table. Not by itself. There is a Y. All right, which of these exhibits stereoisomerism? What would we do? What would be our plan of action? Draw them out, I would suggest, right? So first one, I'm gonna draw. Carbon. 3 hydrogens. So you could draw it like this if you want. What's the next carbon look like? Looking like H and Cl, and then CH. Do any of these have alkenes? What do you think? Welcome back. I don't see any double bonds going on there. I see the octet rule satisfied with single bonds. I don't see any alkenes. So that means that we're not looking for the geometric. We're going to be looking for optical. Is this one that has optical isomers? If you look at this carbon in the middle, that's your option, right? Not going to be the ones on the end. You've got a CH3 on the left. If two groups are the same as each other, that ain't the answer. So far, so good? Check the second one out, B. So we've now got CH3. I usually expand around the carbon of interest is what I like to say, but I'm just writing them all out for you just so you can see. Would it be helpful for you to use different colored pens or highlighters? Maybe helpful, right? That's what I said. Maybe helpful. Which carbon is our best shot? Which one should we be checking?
Carbon 2.
Typically the one in the middle, right? Because the one on the end, this one's got multiple hydrogens, ain't chiral. The one on this side has 2 hydrogens, that ain't chiral. So your only shot is the one in the middle. Check what it's got connected to it. On the left-hand side, you've got CH3. On the top, you've got hydrogen. We're checking B right now. On the bottom end, single chlorine. On the right-hand side, CH2Cl. Are those all different than each other, different atoms? That's the answer. Here's where confidence comes into play. I know that's the answer. I don't want to check anything else. The problem is, if you lack confidence, then you're going to check them all and possibly confuse yourself and waste your time. If you know you have the answer, stop and move on. If you're confident that you're not wrong, then you're not wrong. Yes. Confident and you're wrong? You're confidently wrong?
Yeah, you're confidently wrong or confident?
Well, I hope you're confidently right. All right, we got just a couple more. Geraniol and nerol are compounds found in flower fragrances. All right. Told you there's random fun facts all over here. They're isomers of each other. What do you see? What type of isomerism is shown here? Look for what's different. What's different? Do you see the difference? Point it out.
It's B.
It's around an alkene, isn't it? You have a cis variant and a trans variant. Because what's changing, you switch the H and the CH2OH on the same carbon of an alkene. You have a geometrical isomer, cis trans. In order for it to be positional, the carbon would have had to move to a different carbon in the chain. It is on the same carbon, right? And to be chain, you have to change the length of the carbon chain. You didn't do that. This has to be cis trans. Yes? Okay. Check of 11. Molecule CHBrClF exhibits optical isomerism. Draw the 3D displayed formulae of both optical isomers. Do you remember how to draw tetrahedral? So let's go back over it.
The dashes. I don't think I ever.
Carbon goes in the middle. We need 4 things attached to it. A hydrogen, a bromine, a chlorine, and a fluorine. So the template that you're supposed to memorize for tetrahedral is a line at the top, a line down here because it's 109.5 degree angles, a wedge showing that a group is coming out at you, and then some kind of dashes to show that there's a group going back. Now, the 4 atoms that are here, it doesn't matter which way you place them because molecules are 3-dimensional and they move. Do you agree with me so far? So, what do we want to put at the top? Just throw me an atom. Let's hear it. Okay, sure. What do we want to put here? Why not? Go for it. Down here. Fluorine. Okay, sure. That gives us one option for this one. This has to be fluorine. Right? Okay. if you want to show both optical isomers, which is what's being asked of you here, what you have to draw now is the mirror image. So whatever atom is closest to our mirror would be closest on the other side as well. So here's what you do. Put the carbon, that again, so you're making the mirror image. A wedge and a dash. Notice how I've done it. I'm flipping. I'm literally flipping the molecule. Like flipping my hand. What goes here now? Now you don't have a choice. Something specifically has to go here. Whatever you put closest here has to be closest there. It's like your hand. On the bottom here, what does this have to be? Fluorine. Whatever was on the bottom here has to be on the bottom here. Here has to be fluorine. Here has to be hydrogen. These are the mirror images. You may be asked, and you will likely be asked, because I put less content on this exam to be able to draw this. And I believe I put it on the assignment that I had extended the due date of. I think there might be a question like this in that assignment. So you have to memorize what tetrahedral looks like and draw both mirror images. I'm giving you some time to write it out. Go ahead. And then we just have a couple more practice questions. Giving some time for anybody else who is wrapping up writing this. Okay. Pausing. We're good? On a Cambridge exam, I've seen questions like this. They're typically worth 3 marks. If you remember the template. All right, couple more questions here. Let's do this one and go back to the other one, because that other one is fun. The diagram shows the structure of alkene. Which statements are correct? What does that mean? All carbons are in the same plane. Flat, 2D, everything is trigonal planar. Is that true?
No.
This is tetrahedral. No? That means 3D. This is tetrahedral. So the second one, does this have geometric isomers? Can you flip these two groups and get something different, a cis or a transvariant? Yes. Is it optically active? That's another way of saying it has optical isomers, which means chiral
Yes.
carbon. Does it have a chiral carbon?
Yes. See.
1, 2, 3, 4. Yes. So statements 2 and 3, but not 1. Yeah, we're gonna go back to it. We have 2 questions to go back to, I believe. That we're gonna do now. The fun one, right? All right. So let's go back to the first one that I skipped before, which is this one. Now that you've looked at large molecules, what about this one? This is a cholesterol. So cholesterol, not something you want to build up in your arteries or your older family members' arteries either. Can cause heart attacks. Question for you. Is this actually polar or non-polar? It's got 1 oxygen, but the majority of this is actually non-polar, like most fats. And so it becomes globular and fills up your arteries. So you don't want a lot of blood cholesterol. So go back to this question. It was on slide 12. student X and student Y have made some claims. Are they right or are they wrong? Student X claims all of the carbon atoms in the ring lie in the same plane. Would that be true or false? If you can prove that there are any tetrahedral carbons, this is false. So is it?
Yes, so the wedges and the atoms.
Because like that has 4 groups, right? So no. Student X is wrong. What about student Y? Student Y claims that this molecule displays cis-trans variants, that you can have a cis-trans variant at the carbon-carbon double bond right here. Do you believe that to be true or not? How do you get the ring to go another way? Like the whole thing. Like how do you get that to go that way? If that is that way. So if the alkene is stuck in a ring, you can't just simply move this atom with that atom. Like you can't just switch them. Just like you could with these groups, you could just pop this off and go like, pop, pop. Right? You can't do that with a ring. Try. Like, you know, it's not gonna, you're not gonna be able to make something that exists. So it's stuck. So the answer would actually be here. Neither X nor Y. They're both wrong. Both students are not right. All right, last question to do together. Pentanol C5H11OH has 4 structural isomers that are primary alcohols. How many of them have chiral carbons? This is for you to try. Try drawing them out. This is the last question of the day. Have me check when you believe you have the answer. Show me your work.
4 structural isomers.
Yeah. Huh? You have to show me your proof. The last question of the day. What? Primary means that the carbon with the OH has to be attached directly to only one carbon. So this has to be there. It has to be like this. Well, no. I mean, this is primary. Secondary would be this. You have to have this in your answer. Okay, welcome back. All right, last question is for you all to try.
Interesting.
I'm gonna go C. C never fails me.
Try it. We've got time. Last question of the lesson. It means what?
I need to think.
Yes, brain. You have to use brain cells.
Well, I have like.
You need brain cells for this.
Why did you steal my good rings? Is that where it's going?
Yes. I'm gonna prove the answer shortly.
Your brain is just one big cell.
One tiny little cell. Within a tiny cell.
Can anybody get the answer with the proof? Back? Well, with the proof. I've got some extra, what's it called, candy for anybody who has it with the proof.
Like,
In the next 5
would
minutes.
just the drawing be kind of
No, I'm saying it definitely has.
That's not correct.
Oh yeah, it's definitely not.
No, but like, what if you find it as
Yeah, I need the drawing of the correct
He wants us to draw all the things.
molecule or molecules. The answer is not 0. Do you have an answer?
She has extra candy that we'll get to that.
Also not right. All right. I'm waiting for an answer.
It's not that one.
I do have candy to give out.
Dumb for this.
You're not dumb. You're just tired. Brain hurts. But it's Tuesday.
Well, yeah.
Friday.
There's also the other one.
Oh wait, right here.
I have these like rock candies. Waiting for somebody with a correct answer.
Why are you looking for the charger boy? Yeah. No.
Never mind now.
Sure. No.
You need to win.
First one. Everyone will share their answers. So first one with the correct answer. No hydrocarbon here, because those two hydrogens are the same. Have it yet.
You know, I'm going to.
I will even give the answer away, but you have to have the drawing correct. The answer is B. You have to have one correct chiral carbon.
This is H. All right. So.
That's symmetrical on the left and right side. Secondary one. Not
You
correct.
guys are not at all.
That looks right. About right, right?
Son.
All right. Miss.
It is. We'll tell you not.
Blue.
Wow, your brain works. Wait, stakes get high.
I am so smart. Oh my god. My brain is so massive.
All right, first person got it already.
Can't get in.
Wait, isn't that like this your primary or not? It is not there. All right, I'm gonna give away the answer now since somebody has gotten it. Answer is. Hold on.
Is that true?
Yeah, nothing. He's not giving you your pencil.
I don't think it can be a double bomb.
All right, this is it. So, how would that look? This is the primary carbon, right? Primary alcohol. But the chiral carbon is this one because it's got a CH3, it's got a CH2CH3, it's got a CH, and it's got this. That's the answer. The answer is 1. And this is how could we have also written it? It's skeletal. If I'd written it skeletal, it would look like this. And then this is the 1, and then this is it. This is it in skeletal. Oh my. This is it in skeletal. Check. This is it in skeletal. This is it in like just showing the atoms. Yes. Oh, really?
Just surprised you like them.
That's the only one. If you try to look for another one, you won't find one. Because if you move this here, like if you take this and make it like this, this doesn't have a. It has 2. But no, it's here. Alright, so yeah. Before we go, it is 2:10. So before we go, I wanted to give you a remembrance of what I need you to do. So before next Wednesday, you gotta straight up do the following. Memorize your prefixes. Met, net, pro, bu, tent, text, octomon, vet. You've got to memorize your suffixes for all your organic names and your functional groups. Alkenes, alkynes, alcohols, aldehydes, all of them. Primary, secondary, tertiary carbons. Displayed structural molecular. Functional groups. This lesson and Thursday's lesson. Got a lot to do. We're done for the day. You have homework. It was given to you last class. You can now complete it. I might have a couple. Tutoring is today. I do have a couple extra copies. Pat, do you have the homework? You didn't pick that up? It was given after the class. I have to look for it. I don't think I have the copy. Do you have your copy? All right, put my molecules away, please. Take a small brain break for the rest of class, or build molecules.